All right, in this video, we're going to talk about some particular forces that we're going to be using quite a bit. We're going to see these forces often, and we want to talk about what they are and what abbreviations to use in your force diagrams. We're going to talk also here about making force diagrams and how to label them. All right, so the four forces that we'll see a lot of are weight, normal force, tension, and friction. First one, weight, that is the effect of gravity on an object. Everything has mass, and how hard gravity pulls on that mass is called its weight. We calculate the numerical value of weight as the product of an object's mass times the gravitational field strength. So on Earth, we would use 9.8. On the moon, though, it's 1.6 meters per second squared, or 1.6 newtons per kilogram. All right, and we'll label that in our diagrams. Often I like to use the term mg for weight. The normal force, this is a measure of how hard two surfaces are pressed together. So you sitting in your chair right now, there's the weight of gravity pulling you down, but the support of the chair is pushing up on you. We call that the normal force. So anytime one force pulls an object against another object, the second object will exert a force back on the first object with the normal force. A third force we'll see a lot is tension. So in a string, if you pull something with a string or hang something from a string or a cable, that pulling force of the string is called tension. And lastly, we've got friction. Anytime something is moving or wants to move along a surface, there will be some resistance to that motion, and we call that friction. And we'll see that there's two kinds of friction. Friction when the object is not sliding, and friction when the object is sliding. And these little subscripts here, S stands for static, meaning not moving or not sliding, and K stands for kinetic, which is moving. Okay, so let's take a look at some examples of these forces and how we're going to label them in diagrams. We're going to be making what's called a force diagram, also called a free body diagram. And in these diagrams, we show which forces are acting on a single object. So for example, our first example here, here's a book sitting on a table. It has the force of gravity called weight acting on it. So we'll just draw that in right there. Weight is pulling down on the book, and the table is in the way. If it were not for the table, the book would fall to the floor due to gravity. But because the table is there, it exerts a normal force on the book. Why do we call it the normal force? Well, the word normal here does not mean as opposed to being abnormal. No. What it means is the normal force is normal to the surface, meaning it is perpendicular to the surface. So if this tabletop is horizontal, then this normal force will be vertical. So that's what the word normal means, perpendicular to. Okay, so it's oftentimes too much trouble to draw a picture of the whole book or the whole object that we're talking about. So usually what we do instead is we just pretend that the forces are all acting on the object's center of mass. We know that weight is pulling down on all parts of the book, and the table is pushing up on all parts of the book. But we'll summarize these forces as being equal to a single force acting on the object's center of mass. So that's what that dot is representing. And when we draw our free body diagram or our force diagram of the forces acting on the book, we just draw a dot to represent our center of mass, and then we add in the forces with the tails of the force vectors originating at the center of mass and pointing away. So there's a simple example of a force diagram of a book sitting on a table. Here's a similar situation, a mass hanging from a string or a hanging weight. So of course, the force of gravity acts upon it. Now instead of a table supporting the weight, It's a string supporting it with tension. So for our force diagram, we're going to use the center of mass. So all you have to do is draw a dot that represents the center of mass of the weight, and then label it with the two vectors of the forces acting on it, the force of gravity, or the object's weight, and the tension in the string. So you see this is a very similar diagram to the previous diagram. In both cases, the object is just sitting there and not moving. And that's because, as we're going to learn with Newton's second law, these forces cancel each other out, or we say they add to zero. So there's no force, no net force to cause the book to accelerate. So in this diagram, we see that the net force acting on the book is zero. In other words, the vector sum of the normal force and the weight add to zero, just like in this diagram, the vector sum of the weight and the tension add to zero. In this next example, let's look at a box being pulled across the floor by a horizontal string. So, of course, the box has weight. The floor supports the weight of the box with the normal force. The string has a tension in it, which I'll call a pulling force, F sub P. And anything that's sliding on another surface experiences friction. And so I'll just call that friction. And when we draw our force diagram, remember we pretend all those forces are acting on the center of mass of the box. So we just draw a dot to represent the box. There's the normal force supporting the weight. There's the force of gravity pulling down on the box. There is my pulling force pulling the box to the right, and the frictional force, which is opposing the motion of the box to the left. We'll see that friction always opposes motion, or if something wants to slide in one direction, friction will oppose that as well. So here is my force diagram for a box being pulled across the floor. Four forces acting on the box: the force of gravity, called the weight, the normal force, which is the support force of the floor, the pulling force. We could have labeled this T for tension in the string. That would have been fine. I just chose it to call it FP for force of the pull, and the friction, which is opposing the sliding motion of the box across the floor. Let's look at another example. Here, I pushed a box, and it is sliding across the floor. Okay, so while the box is sliding, I'm no longer pushing on the box. So now there are only three forces acting on it. The weight and the normal force are still there, of course. But now I've pushed the box to the left, and so I notice that I have misdrawn my arrow here. Okay, so the frictional force then is going to oppose the motion. The motion is to the left, so my frictional force then will be to the right. So when I draw my force diagram, I just start off with a dot representing the center of mass of the box, the normal force from the floor, the weight from gravity, and the frictional force, of course. That force is going to be acting to the right because that opposes the sliding motion to the left, and I would label that F. All right, here's another example. This is just a box sitting on, instead of the floor, sitting on an incline. So a little ramp. I've built this little ramp, and the box is just sitting still on the ramp. And this is a little different from it sitting on the floor in that, remember, well, it's still the same in that it has weight. Okay, so the weight is still straight down. Weight is always a vertical force. But now the difference is the normal force. Remember I was telling you the normal force is perpendicular to the surface. So this ramp is at an angle to the floor, and so the normal force is perpendicular. I could have drawn that a little better. Is perpendicular, there we go, to the surface. Okay? So you can see now the weight and the normal force are not pointing in exactly opposite directions. We still use the center of mass to represent where the forces are acting upon it. And now we see that the box wants to slide down the ramp. We know that things would slide downhill. But if it's just sitting there, we know there must be some force preventing that. And that is the frictional force. And I've labeled it this time with the letter S because it's static friction. The box is not sliding. So the frictional force exists between surfaces that are at rest with respect to one another. Okay, so these three vectors will add to 0. I know that because the box is not accelerating. And anytime there is 0 acceleration, there is 0 net force, which means the sum of the forces equals 0. And of course, if I was drawing this on my paper with a simple force diagram, it would look like, like this. There's the weight, the normal force, which is acting perpendicular to the surface, and the static frictional force. It opposes motion or it opposes possible motion. So we know that it's possible the box could slide down the ramp. So the static frictional force is the force that opposes that motion. And in this case, the frictional force is large enough to prevent it from sliding down the ramp. And these three forces add to 0. We're going to look at adding forces in more detail a little later. Let's look at yet one more example. Now I've raised the ramp to such an angle such that the frictional force can no longer keep it from sliding down the ramp. And I raise it to a level, and now the box is sliding down the ramp. And now the forces acting on the box are very similar to what they were before, except now I've got kinetic frictional force. And again, it opposes the sliding motion of the box. Down the ramp is the sliding, so up the ramp is the frictional force. And my force diagram that I would draw on my paper would look like this. There we go. For our last example, we'll look at a swinging pendulum. Here we see there are two forces acting on the pendulum bob. There is the gravity, the force of gravity, the weight, which always points vertically downward, and the tension in the string, which always points in the direction of the string. If we set our coordinate system so that the positive y-axis is always along the string, we see that at the lowest point of the swing, neither of these forces has an x component. So the sum of the forces in the x direction is 0. When forces sum to 0, we say the object is in equilibrium. So this lowest point of the swing is referred to as the equilibrium point. At the equilibrium point, there is no net force in the x direction. So there is no acceleration in the x direction. At any point in the swing, other than the equilibrium point, we see that the weight will have a component of force unopposed in the x direction. We also see that the component is always back towards the center, attempting to restore the pendulum bob to the equilibrium point. For that reason, the x component of weight is called the restoring force.